Hello everyone, this is Akshay Jain, Master Student Electrical and Computer Engineering Department, University of Florida, and today I'm going to talk about radar-assisted pixel-based object tracking algorithm. Below is my webpage. You can anytime go and see my profile on that. So moving forward, we discuss the problems at hand. So the problem I'm considering is tracking an object using a key. So the intuitive so if you think about it intuitively, the problem which we face first and foremost is that we have very few pixels to track on, and but if we have very few pixels, you can't possibly apply the spatial techniques which are very profound in today's object tracking algorithms. Another problem which in general the object tracking algorithms face are the interfusion, collusion, and loss of target in presence of similar objects, and these statistical procedures which are very popular among today's object tracking algorithm techniques, they may be time and resource consuming, as they might require a large amount of computation, and sometimes in the presence of complex environments they might not be accurate. So these are the problems which we have on our hands, and the very basic problem I'm considering is tracking using an UAV. So why do we do object tracking? Well, surveillance it's a very useful technique to do surveillance actually, because you can have a real-time track of the object, and it has been facilitated, its growth has been facilitated, I should say, uh, by the technical developments in the lens technologies and the video transmission and storage techniques. And henceforth, instead of a still image tracking algorithm where you might have a large sequence of images and then you need to look at one at a time, instead you can have a real-time tracking using a video capture. So we now have the motivation, why are we doing object tracking, and what is our problem at hand, and so we move forward. But before discussing the solution to the problem of tracking using a UAV, I'd like to discuss a few other approaches, which are: one is the mean shift algorithm, which is very popular and kernel-based algorithm. It seeks the mode. The next is the covariance matrix-based algorithm. It tries and develop a covariance matrix about the object to be tracked in every frame, and so it gathers the statistical properties and the dependence in each and every frame, which is a pretty good method but requires a lot of computation. The pixel-based k-means clustering algorithm is another very good technique which utilizes the clustering approach using the k-means clustering and has an update procedure which I am going to discuss. And the block matching based algorithms are crude way of determining the presence of objects. These are the brute force algorithms, and they require the matching of a template in every frame, and these are very computationally intensive, not viable for real-time problems. So I'll discuss the mean shift algorithm first. So it's a mode seeking algorithm. It seeks the mode of the density function which we consider to model our color distribution. And so the color distribution model is basically the kernel, and then it tries and develop a similarity measure by calculating the probabilities of the colors in the bins of the distribution model, as the colors, I should say, the colors in the histogram, colors in the bins of the histogram for the distribution model considered, and also for the actual distribution which is present. And it iteratively tries and converge these pixels towards the modes, and in this way it iteratively clusters together all the target pixels. So it is a continuously it continuously updates the modes, and continuously tries and converge the other pixels, or you may say the unknown pixels, towards these modes. The next is the pixel-based k-means clustering. So algorithm basically distinguishes the pixels as target and background. So you basically have two categories, the target and background. It fixes the radius, or it fixes a shape called maybe an ellipse, in which it considers the object to be present along with some amount of background pixels. And so it utilizes the k-means clustering approach, wherein it specifies the candidate pixels, and for the background as well as it. And then the other unknown pixels, by using the k-means clustering approach, are clustered either as the target pixels or as the background pixels, and that is done using a dissimilarity and a similarity measure, wherein the spatial as well as the color details are utilized. So it is very resilient to changes in color, which may be due to shadows or due to some amount of interfusion of objects if it is not rigid. So it's very rigid. And it also specifies an update mechanism wherein it considers the distribution of the pixels of the object to be Gaussian, and then it utilizes the Mahalanobis distance measure to actually update the search area. So with the help of a formula, which is with the help of a formula, they determine a Mahalanobis distance, and using this Mahalanobis distance, they then try and reassign the pixels new coordinates, and then you again go back into an iterative procedure wherein cluster the unknown pixels. And so this is how this pixel-based k-means clustering algorithm works. These are the two better algorithms which I found. And so moving forward, well, both of these algorithms, and for instance, and as a matter of fact, the other algorithms which I just listed out, they are basically spatial techniques, and they are prone to a large variety of problems. Like you have an incorrect model. Modeling is not an easy task. It might turn out to be wrong, or color interfusion, as well as the degree of the object motion. Object motion is a very, very big problem for a lot of techniques, because they are rendered incorrect sometimes by sudden motion of objects in either direction, or and so that's a big problem. So I thought out that why not use the Doppler shift to actually track the object. So motion of an object, if you so we all know that when an object is moving, and if it sends out some kind of sound waves or any kind of waves, they encounter they experience a Doppler shift. Any object which is observing the moving object, and if it's sending out some kind of a wave, the observer will will experience a Doppler shift. And so in this algorithm, I try and utilize that property, and with the help of a pulse ranging technique with a narrow beam width radar, that would suffice our cause, and so that would actually suffice our needs. So moving forward, well, first of all, I tried and performed a observational study, and that is to check whether the pixels are Gaussian distributed, because we need a search area when assume the pixels to be present. So with a standard deviation 1, I carried out the pixel. I distributed the pixels with and kept the mean as the pixels themselves and the standard deviation as 1, and applied a Gaussian distribution, and then relocated the pixels according to that mean and standard deviation to their new location. With standard deviation 1, the mean square error per frame came out to be 4.3 into 10 power minus 3, and with standard deviation 2, it was 5.4 into 10 power minus 3, which is pretty low. And as you can see, the object is near about the same, with with some amount of distortion due to the relocation of the pixels, which might be due to the relocation of the pixels, and so still it's pretty much and so we can say that the pixels are Gaussian distributed actually. So moving forward, yes, now we discuss the scenario. So as I said, the problem I'm considering is that we have a UAV on top, and it is at a very large height, and we have an object at the bottom, and we have very few pixels, and so we are trying to use a pulse ranging technique, which uses there is a radar which is assumed to be there on the UAV, which has a narrow beam width, and it is able to provide us with a Doppler shift value, as in when we send a pulse towards the object, and when it returns it back, it observes the returned frequency, and then we are able to calculate the Doppler shift because the transmission frequency, and we just observe the return frequency. And so this is the problem at hand. So we have a UAV which is transmitting a pulse to the object, and it is returned back, and utilizing that we are trying to track the object. So what is the Doppler shift? Well, the formula is as written above. It is the change in frequency is the relative velocity times the transmission frequency whole divided by the speed of light. So I'll just try and explain you why the Doppler shift happens. So when we have a transmitter A sending out a wave at some frequency, say f, the receiver B, and if the object A starts moving in the direction of B, so what happens is when it sends out the first crest, it takes some amount d, it has to travel a distance d, and say it takes time t to travel this distance. Now when it is about to transmit the next crest, this object is over here, and when it transmits the next crest, the distance d prime is smaller than the distance d, and so the time t prime would be less than the time t. So as in when it observes the first crest, it takes lesser amount of time to observe the second crest, and so the frequency goes on increasing as the object nears, and vice versa when the object moves far away, because the crests then start to take longer times to reach the object, and so the frequency of observed frequency starts to decrease, and so that's why we have the Doppler shift phenomena. So moving forward with this background, we start our algorithm with an initial vicinity search. So to perform the initial vicinity search, what we do is we take a template. Now we do not know where the object is within the whole frame, so what we do is we assign the borders as the initial search places, and we search throughout the borders for any sort of fragment of the template is present. So after the search is performed using a correlation measure, a two-dimensional correlation measure is performed, and the block with the maximum, or the shift, because we are shifting the block throughout these rows and columns on the edges, and the shift which produces as the maximum correlation is taken as the reference point for the next step of the vicinity search. So say box 3 row is selected with the maximum correlation. So what we do is then we perform another second stage vicinity search, where it is just confined to the blocks above and the blocks to the right, and the whole rectangle which would be encompassed if we went round and came back to that to the initial box. And so after performing this vicinity search, we are able to detect the presence of the template and presence of the object which is specified in the template, and so in this way we are able to search the object in the first frame. This is the first frame search, which is the initial vicinity search, and this is the most time consuming part of this algorithm. We move forward, and now the most important thing is Doppler generation. Well, you might have thought that the Doppler effect is quite simple to model, but it's not, because we do real-time scenario. And so to model the Doppler effect, what I've done is I've actually utilized the correlation properties between the template block in the previous frame and the next frame, and try to analyze where the object lies in the next frame, and the displacement of the object in one direction actually can be thought of as the movement of the object with respect to the with respect to our UAV in some direction, and then we can assign a relative velocity. So this is a very crude procedure to actually model the Doppler effect, but this is the only way. So what I do is I take the block which has been detected with the object block which has been detected in the current frame. Moving to the next frame, I perform another vicinity search, which is like to the north, northeast, to the northwest, to the south, to the southwest, to the southeast. The east and the west directions do not produce a lot of change in the Doppler effect, as they are moving perpendicular to each other, and so it can be they don't produce a lot of change. The main purpose of this algorithm is that even if they move to the right or to the left, they can be modeled very easily. So we determine the Doppler shift according to the movement of the template block in the previous frame to the current frame. So the blue block is the one which is detected in the previous frame, and the red block shows us that the block is now moved to this position. So this movement is a forward motion, and considering that our UAV is at a stationary condition, this is a forward motion. A forward motion creates a negative velocity, and thus it decreases the frequency of observation, and so there is a negative Doppler shift, and vice versa. If it would have moved back, then there would have been a positive Doppler shift, a positive relative velocity, and so in this way the Doppler effect is generated. And to find out the blocks, we utilize the correlation again, the two-dimensional correlation. So this is how the scenario is generated for Doppler. Moving ahead, the final search. So once you have found out the Doppler effect, you know where your object might lie. If it is a positive Doppler, it might be either to the north, to the northeast, or to the northwest. Or if it is negative, if it is negative, it might be to the north, to the northeast, or to the northwest. Or if it is to the south, it might be the Doppler effect is positive. To the south, southeast, and southwest, the Doppler effect is positive. So we have the blue block, and we have found out that the direction of motion is to the southeast. So the red circle indicates the trimmed search area. We need not search in every direction. That is the trimmed search area. And so we just take a look at either the south or the southeast direction, and the shift of the block which produces the highest correlation gives us the presence of the object in that frame. And so in this way we can, and then the next reference template is updated to the current detected block. So the current detected block becomes the next reference template, and then you again perform the same procedure, but you take into account the Doppler shift every time, because moving forward, yes, the results. So as we can see, in frame 1 we have detected the object we have detected the object successfully, and it is shown using a white detection box, which I call. Now the object doesn't go into motion from frames 1 to 40, so I have skipped those frames. In 40 it starts its motion, and we are still detecting the object. In frame 45 you can see that the white detection box is starting to lag a bit, because it does not have the accurate Doppler frequency with it. A correlation measure is not an accurate way of measuring the amount of velocity with which it is moving, and so it starts to lag a bit, but we are still able to track the object. And in frame 48, when it comes to rest, we are still able to move along with the object, although with a bit of lag. So we need an accurate modeling of the Doppler effect, but this algorithm proves to be very effective when we have the accurate Doppler frequencies with us. So still the object is tracked, and it is tracked very efficiently in the right direction. However, there are possible enhancements to this technique, and so one of them is like increasing the number of frames by interpolating in between two frames, and this makes the motion of the object much more gradual, and then you are able to detect the object much more efficiently. It reduces the errors. And the next is modeling of the angle of arrival of the EM waves. And so the point is that when you know the angle of arrival of the EM waves which are reflected and which have significant energy, which is what you will receive from the object, and the clutter is basically very weak in nature, so by measuring the angle of arrival you can actually have a beforehand knowledge of where the object might be, and you can prune your search area further, and that can reduce the amount of computation you need to perform to search the object. So that's another enhancement. In this project I have just laid out the first enhancement, that is I have increased the number of frames through interpolation. And so we take a look at what I have done. So the methodology is that we take the difference between adjacent frames. So if there is no motion, they should be exactly zero. There should be no motion. If there is no motion, they should be exactly zero. And if it is non-zero, then there is some motion there. So between two frames where there is motion, we put in another frame, and this is created by differentially weighting each of the pixels, the previous frame and the next frame with respect to the frame which we are inserting. So say if t minus 1 was the previous frame, I weighted by 0.9 in this project, and the next frame by 0.05, which is an optimal solution which I had found by doing some sort of balancing effects, because see, the previous frame is always going to depend a lot more on the previous frame rather than the next frame. That is why the ratio is so acute between the previous frame and the next frame. And so, as I've also stated, the current frame always depends more on the previous frame. And so after that, we carry out the tracking application according to the methodology defined earlier. And the output, I've shown just one frame to just show you that the optimization tried works properly, but still it lags, and that is again due to the fact that we don't have the correct Doppler measure which can actually model these things. And so a correlation measure is never good, and we are fixing frames in between, so the correlation measure again starts to like, it does not show a lot of difference between adjacent frames as you're fixing frames in between. The correlation starts to go to 1 in every trial, and so that is why you don't have accurate tracking. But still it's able to track, and it's able to track properly initially, but not towards the end due to the poor numbers which we have. But nevertheless, the problems encountered are the Doppler input is not real time, and so the algorithm lacks the precision in the output. Also, the differential weighting of the frames needs to be modeled in order to have better optimization, because you need to determine the weights properly. So these are the problems which I encountered, but still the object is tracked properly, and we are able to track the object properly. And one more point, when observed very closely, the direction in which the white detection box moves is much more better than what it moves in the previous defined algorithm, and so you can say that the optimization works to some extent. So also the differential weighting of the frames needs to be modeled properly to have, so 0.9 and 0.05 are numbers which are purely based on the fact that the previous frame has to contribute more to the next frame than the frame after the interpolated frame, and so that's why. But we need some kind of a much more optimized solution for that. So the conclusion, well, it is more real time. You have got a real time Doppler effect, Doppler shift measurement, and you can track your object on the fly very quickly, because you just need to determine the pruned search area and then just track the object. It is bereft of any spatial and statistical dependencies, and hence less error prone. And so it's just that you determine the direction very accurate of the object where it is going, and then use the correlation properties instead of from the start itself you use the statistical and the spatial properties of the object. That can lead to errors because they are not always well defined, or they might have some kind of problems such as interfusion or shadowing or something. So yeah, the Doppler effect helps to model these, helps to define the search area much more effectively and much more accurately. It is very easy to implement. You just need the Doppler shift and you can search the object, and it is able to track of orientation change which the object might undergo. So as I told you, it can model any kind of directional changes because the Doppler shift changes according to the direction, and if you model the angle of arrival, you have a much higher resolution. And it can be implemented using UAVs with a narrow beam width radar, which is our task. So yeah, I've shown that you can use a Doppler shift algorithm, Doppler shift technique to actually track the object, and it can be used on UAVs because radars have a good resolution property even in long ranges, rather than utilizing the very less amount of pixels you have from such a great height. So that's it. Thank you, and I'll now show you a simulation of my project. And so just a minute. to MATLAB. These are the files. This is object tracking file, and I'll simulate it and run the simulation. Sorry about that. So this is object tracking file, this is a scenario file, this is the this is a file which is used to do the optimization part of the project, and this is the optimization main code. So we have got a simulation running. It's busy. It's rendering the GUI for the movie player and loading the data source, and here we have. And so I'll start the simulation with 72 frames. Here we go. You can see it's tracked the object detected, and we have tracked the object, and that's the end of the simulation. So that was the presentation on radar assisted object tracking algorithm. Thank you.